And now one last thing for today, using the dot product to find angles between vectors. Now this is really quite straightforward. We don't really even need to do a whole other video for it, but let's just make sure, because this concept is new, we've really explored it from every angle. All you need to do is just rearrange the geometric formula for the dot product. So that formula looks like this, and it's got cos theta in it. So clearly, if you want to find cos theta, you can do that if you know these other parts of the formula. And you can just sub in what you know and then rearrange it, or you can rearrange the formula at the start and then do your subbing in. So we can see that cos theta will just be the dot product divided by the lengths of the vectors, and therefore theta will be the inverse cos of all of that. So a really simple example to start with, we need to find an angle theta between two vectors. We're given the lengths of the vectors, and we're even given the dot product. So there's not too much to do, but it's a good idea to actually write out your formula. Now, if you want to write it out this way and then sub in, that's fine. Or if you want to get used to writing it like this as well, you can. I would tend to think that this one is on your formula sheet. So if you've got your formula sheet beside you, you can see this. So then it's very easy to write down your first line. Cos of theta is equal to the dot product. Oh, not A and B, it's U and V, isn't it? So let's put the right letters in there. We've got U and V over the length of U multiplied by the length of V. Now, writing that down, yes, I can almost hear you saying, why do I have to write that down? But every single time you write it, you're getting more and more familiar with the formula, and that's going to help you. So now we have the cos of theta equals -5 over 2/4, which is 8. So then theta will be the inverse cos of that. Now it's not an exact one, so you'll need your calculator. And the inverse cos of -5/8 is to the nearest degree 129 degrees. So I'll say that that's to the nearest degree. And then if I like, I can even say it's not exactly equal. I can use the dots, or I could use the squiggly equal sign. If I was working in radians, then I'd be really clear about it. So if they haven't told you whether to work in degrees or radians, then take your pick and just explain what it is that you've done. Okay, a slightly trickier example now. We need to find the angle in radians to 1 decimal place between these vectors. Now they're both in component form. If you like to write them in column form and literally translate them so that they look like this, feel free to do it. It's probably not essential, and it's good to be able to work in either column form or component form. But remember, if you're struggling with this, it's exactly the same as this. Now, to use our formula, we're going to need to find some things first. We need to find the dot product, and we need to find the lengths of our vectors, because we don't have any of that information yet. So let's find the dot product first. Now the dot product is easy to find. We just need to do the x's multiplied together and the y's multiplied together, and that gives us 13. So that was quite straightforward. Now, to find the lengths of our vectors, two strategies. One is you can just apply the formula, which says you need to do the x squared plus the y squared, and all in a square root. Now, this is just Pythagoras' theorem taken into a shortcut. But if you're one of those people that will forget formulas, or you think, oh, hang on, is it squared or not squared? Is it the square root? Then literally you can just draw it. So applying the formula here, I can see I need to do 3 squared plus -2 squared. So that's going to give me 9 plus 4. I need the square root of 13. But another way I could find the same thing is just to step it out. This vector means I'm going 3 steps to the right and 2 steps down. And that's so easy to draw. 3 steps to the right, 2 steps down, and now here's my vector. And I think as quite a visual learner, I'm less likely to mess it up if I actually draw the vector and then just think about how long this side is. 3 squared plus 2 squared. I'll do the exact same thing in my head and I'll get this same answer, but I feel a little bit more sure of it when I draw it for some reason, but maybe that's just me. Now we need to do the same thing for the other one. Now we could apply the formula and say we've got 5 squared plus 1 squared, go through this same process. I prefer just to step it out. I'm going 5 steps to the right and 1 step up. Perhaps I'll put my steps down here. And so I've got a vector that looks like this. So 5 squared plus 1 squared is 26. So this side must be the square root of 26. So both of those are quite easy to find. Use either method, whichever one makes sense to you. Now I can go ahead and apply my formula. The cos of theta is the dot product. Now writing this out every time is not a bad idea because you'll just get used to it. So we've got this, And now we know each of those parts. We have our dot product, which is 13, over our square root of 13 multiplied by our square root of 26. Now, for different questions, this one I can see I need to be in radians mode. So first step is get in radians mode and double check that you are. Good. But if I hadn't been told it was a radian, it was in radians to 1 decimal place, there's a chance I might be asked for this in exact form. So if you're going to get some mucky kind of term here, it might make sense to simplify it up, because you'd be amazed how some nasty looking surds can often multiply out to make something that will tidy up to be quite a simple term. So on the bottom here, let's tidy it up a little bit, just for good practice. 13 26s is 338. And you can see that if this number here could actually talk to this one, or potentially it could even be a perfect square, you'd end up with something simpler here. Now, writing down each time what this is equal to is not a bad idea, because if you just write equals, 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 it's easy to get something, you go, there you go, ta-da, I finished. But no, we haven't found the angle yet, we've just found the cos of the angle. So finishing it off, the angle is going to be the inverse cos of that fraction. So I have 13 over, oops, I messed it up, 13 over the square root of 338. And I'm going to get 0.1 decimal place, let's say it's 0.8. Now this is radians. Do I need to write radians? Not really, because radians are a ratio. If you want to write radians just so it's really clear that it's not in degrees, it's not wrong to do it, but it's not essential for it to be there. Now when you get to the end, think about whether your solution actually makes sense. I've drawn vector A and vector B here just roughly, but if I drew them with the same tail, then if vector A is here and vector B goes across 5 and up 1, it would go across 5 and up 1. It'd look something like that. So I'd have vector A here and vector B there. So looking at what the angle would be and just sort of guessing if it looks around about right, I know that 1 radian is roughly 60 degrees, not quite, but this sort of angle, it's going to be 45, 50, something like that. And even just a rough sketch like this, I can see that it looks right. And checking again if I've answered my question makes me realize that I should have written that this is roughly equal to 0.8 radians, or I could write that it was equal to 0.8 radians to 1 decimal place, just my disclaimer then as to how I've rounded it off. You could even put the disclaimer with the wiggly equals if you need to, and remember you don't essentially really need to write radians either. And one last example that's quite different, we need to use the dot product to find the angle ABC if we're just given the coordinates of these 3 points. Now this is on a Cartesian plane, so to me it makes most sense to start with a quick sketch. It doesn't need to be perfect. If you've got graph paper, use it because it makes the counting a lot easier. But even without graph paper, if I just go ahead and put in point A here at 3, 2, and point B can be at 7, 4, so let's put that over here, and point C is at 2, negative 8. Now it only has to be roughly looking right. Now I can go ahead and make my triangle. Now the angle that we're looking for is ABC, and that means we want this angle up here where it's revolving around the B. So I need to use my dot product because I've been asked to do it that way, and I also need 2 vectors that have the same tail. So that means I need a vector here going this way and a vector here going this way. So if I define this vector here as BA, and we can just call it that, we don't need to give it like a squiggle or something like that. We can just say vector BA, and now we can find the vector, I think in column form probably makes most sense. Now again, step it out. How do you get from B to A? If you're instructing someone how to get there, only going left, right, up, down, it looks like you need to go 4 units to the left, so that's negative 4, and you need to go 2 units down. So that was really quite straightforward. And then BC as a vector to go from B to C. Well, how do you get there from here? Well, you need to go from 7 across to 2, so we need to step 5 steps to the left, and then you need to go from 4 all the way down to -8, so that's a distance of negative 12 because we're going down. In fact, this one should have been -2. Hopefully you spotted that. So we're going left and down to get to both points. So all of these are negative numbers. So now we can find, we're going to need the absolute value of each of these. So to find that, we need to do 4 squared plus 2 squared, which is 16 plus 4. We've got root 20, which is the same thing as, what's that, 2 root 5. And to find the absolute value of this one, we need to do 25 plus 144, which is 169, and the square root of 169 is exactly 13. This is a 5, 12, 13 triangle. And just checking that it looks right, this is 12, this is 5, so sure enough, if you like the method of finding these where you just sketch it, we've already got a sketch. So we can picture that we've got 12 here and 5 here, and for this one we can see that we've got 2 here and we've got 4 there. What next? We need the dot product. So the dot product of BA dot BC is going to be, now to find these dot products we need to multiply the x's. So -4 times -5 is 20, and then multiply the y's, and that gives us 24. So nice neat answer of 44. So now we can say that the cos of theta is equal to the dot product, which is 44. Okay, you'll notice I'm not bothering to write out the formula this time. And on the bottom, I need 2 root 5 times 13. So I need 26 root 5. Now, feel free to tidy that up if you want to. I can see that that's 22 over 13 root 5. A little bit neater. And now theta, it hasn't told us. Let's go degrees this time. So let's go into degrees mode. And we need to find the inverse cos of 44 over 13 root 5. Sorry, it's 22 over 13. I'll get it right. 22 over 13 root 5. And in degrees, we get 40.8. So let's go degrees and minutes. We've got 40 degrees and 49 minutes to the nearest degree. And if you've rounded it off, sorry, it's not the nearest degree, it's the nearest minute. I'll get it right in a minute. So the nearest minute, and if you want, you can say it's approximately equal to, but if you've used this disclaimer here, it's probably okay also to use the equal sign, depending on how fussy you are. You might like to use the almost equals and the disclaimer, up to you. And when you finish, you should always check whether your answer seems to make sense, and even on my very rough sketch, 40 degrees looks around about right. Now, you'll notice that you don't need vectors to answer questions like this. We could have used the distance formula just to work out the distances of each of these lines here, and then we could have used the cosine rule. Why didn't we? Well, sometimes the working with your vectors will actually be quicker and easier. And again, we're just learning another method to do the same thing so that we've got lots of tools in our toolkit and can pick the one that we want to use each time.